Today we're going to start chapter 4, which is on probability distributions. So taking what we've already learned in chapter 3, but really extending it a little bit further. So first, some definitions. Random variables. The outcome of a probability experiment is often a count or measure. When this occurs, the outcome is called a random variable. A random variable x represents a value associated with each outcome of a probability experiment. The word random indicates that x is determined by chance. And there are two types of random variables. We have discrete random variables and continuous random variables. A random variable is discrete when it has a finite or a countable number of possible outcomes that can be listed. So your discrete random variables, you can actually list the outcomes. So they're either finite, meaning that eventually you stop, right? So there's only 10 of them or 20 of them or 100 of them. So there's a finite amount of them. Or they could be infinite, but they are countable. So we have a way that we can actually still list those numbers or those options, even if they are infinite. You also have random variables that are continuous. So when we have something that's continuous, we actually have an uncountable number of possible outcomes. So you do have this idea of infinity, but it's more than just that, because you can have this idea of infinity with discrete. But here we actually could not count everything or even list all the options. What we typically do instead is use some sort of interval or on a number line to represent them. In most applications, you're going to see that discrete random variables represent data that can be counted, while continuous random variables tend to represent data that is measured. So those tend to be the big differences. Let's see. For instance, consider the following example. You conduct a study of the number of calls a telemarketing firm makes in one day. So think about this. You're counting how many calls that company makes. They could make 0 calls, 1 call, 2 calls, 3 calls, 4 calls, 5 calls, 6 calls, etc. Right? So, but our only options in this particular case are calls, right? We're not going to do half a call or a quarter of a call. That doesn't make sense. So even though our numbers could keep going on forever here, we can still list them and show that pattern. They're countable. So these are our possible variables. Because we can actually list the set of outcomes, this is a discrete random variable. Now on a number line, what this looks like is this. Okay, so I'll just do a few digits on the number line. So our possible values for x, so for the number of calls, would be 0 calls, 1 call, 2 calls, 3, 4, 5, 6, and so on, right? So only those whole numbers there are counted in this case. What you do know with discrete random variables is that you will see gaps between these data points. With discrete variables, and that's a really big thing to watch out for. So if you have gaps between the possible data points, then you have discrete variables. Now, they don't always have to be just integers or whole numbers, although that's what happens most of the time. You could still have fractions here, but there still has to be gaps. So for instance, if we're going back to that chocolate chip cookie project, right? If you're counting numbers of chocolate chips and cookies, some students count down to the half chip or sometimes even the quarter chip. So your data could be, let's say we use half chips, 20, 20 and a half, 21, 21 and a half, 22, 23, 22 and a half, and so on, right? So you could have all these different data points that do include some fractions. But the key is that we're not including all possible fractions. We're still limiting which fractions we use, and we're still causing gaps between the data, right? So if we're counting chocolate chip chips in our cookies, maybe I allow 20 chips, 20 and a half chips, and then 21 chips, but I'm not allowing in between, right? I'm not going to allow 20.12 chips or something like that. So we still have discrete data there, even though we're allowing for fractions, because we have gaps between the data points. Another example, and this one's going to be continuous, is instead of studying the number of calls, maybe we want to measure the time spent in hours making calls in one day. Now, the time can be anywhere from 0 to 24, right? Theoretically, right? You make 0 minutes or 0 hours of phone calls all the way up through 24 hours of phone calls. Maybe you have a company that you're staffed 24 hours a day, so you always have somebody working. And you could include any sort of fractional decimal in between here, right? So maybe the answer is 5.21346 hours or something like that. So because we're measuring the data and we're allowing for any data point within this interval from 0 to 24, this is continuous. So on a number line, so I'm going to do 0, 6, 12, 18, 24, and then let's see, 30, and so on. Then what I would have here is my possible values are anything between 0 and 24. So visually, we have an interval we're looking at here, not just individual data points. So that's your difference. Again, when you're looking visually at it, for discrete data, you're going to see gaps in between. Even if you're allowing for some fractions or decimals, you're still going to have gaps. When we have continuous data, there's no gaps, meaning that we will allow for any data point in between here, any fraction, any decimal to occur, and it would be fine. So let's determine whether each random variable is discrete or continuous. So let X represent the number of Fortune 500 companies that lost money in the previous year. So if you think about this, the number of Fortune 500 companies, well, that lost money in the previous year, well, possible values could be 0, 1 company, 2 companies, 3 companies, 4 companies, 5 companies, and so on, right? So we have all these different possible answers, and this could go on theoretically infinitely long until we hit the maximum of Fortune 500 companies, which would vary depending on the year. But you have distinct gaps here between the data. So if you were to graph this, it would look very similar to this graph here, right? We're not going to have half a company or a fraction of a company. It doesn't make sense. So you have clear, distinct gaps between those data points. So this is something that is discrete. Now for the second one, we're going to represent, X represent the volume of gasoline in a 21-gallon tank. Now here we're talking about volume. Volume is something that we can measure. So a lot of times when we have things like heights or weights, volume, we often measure those things instead. Obviously, it's going to depend on your example. So every example could be a little bit different. But typically when we have things like that, we tend to measure and allow for those fractions and those decimals in between. So same thing for volume. We can measure volume. So in this case, this is going to be a continuous data set because we can allow for any fraction in between. So if you have your number line here, theoretically, we could go from 0 gallons, so your gas tank is completely empty, up to 21 gallons, meaning it's completely full, and anything in between would be okay. So we could consider fractions and decimals. I know when I fill up my gas tank, very rarely do I get an exact number of gallons, right? So it's always like some decimal in there. So we can definitely measure our volume here. So we have continuous data. Now, we're going to focus on discrete probability distributions in this chapter for the remaining of the chapter. And then in the next chapter, we'll focus on continuous distribution. So we're breaking up the examples a little bit now, so we can look at some examples that are discrete, and then later on in chapter 5, examples that are continuous. And the reason we do that is because they really do use different statistical techniques. So they have a lot of similar ideas in common, where they're both going to be probability distributions, and are working with probabilities and things like that, but we do the calculations in different ways when we can count something versus when we cannot count something. So for the rest of our chapter 4, we're focusing on these discrete random variables. Now, each value of a discrete random variable can be assigned a probability. By listing each value of the random variable with its corresponding probability, you are forming a discrete probability distribution. So basically, this is sort of just like a table that lists all your possible X values and then next to it, what their probabilities would be of occurring. So that's all it is. It's really just a table that has your possible X values for those outcomes, and then what the probability would be of each of those outcomes occurring. That's a probability distribution. And that's discrete because we actually can list all the outcomes, right? So we can't always do that with continuous. We can't list our data, but we can with discrete. So we can actually list every single outcome. Now, things to note, discrete probability distribution, again, lists each possible value that the random outcome can assume together with its probability, but it also must satisfy these conditions. So first of all, keep in mind that any probability has to be between 0 and 1, right? So we saw that same rule from the previous chapter. Probabilities cannot be more than 1. They cannot be less than 0. And then the other thing here is that when we talk about all possible outcomes occurring, then the sum of those probabilities has to be 1. So you have to get that full 100% of everything that could happen. And that's the same thing here. So when we add up our probabilities, we should get the value of 1, meaning that we have accounted for every single possibility, right? That full 100% is accounted for. It's going to add up to 1. Now, we can also graph our discrete probability distributions, and we would graph them the same way we would graph a relative frequency histogram that we learned already about. So really, it's very, very similar to those relative frequency tables and relative frequency histograms. So we're doing very similar calculations. It's just that instead of using classes, we're talking about individual outcomes. Okay, so you have some steps here for how to construct a discrete probability distribution. So we're going to just go through it together with an example. And then on the next page, I will show you what the graph looks like as well. All right. So this is in your text, of course. If it's a little hard to read here, you can feel free to go to your text to see the example in larger print. And it says the following. An industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a whole number score from 1 to 5. 1 was considered extremely passive, and 5 was considered extremely aggressive. A score of 3 indicated neither trait. So if you earned a 3, then you were neither in the passive category or in the aggressive category. You're still kind of neutral. And the results are shown in the table on the left. So here are your results from that survey. So 24 people were given a 1, 33 people were given a 2, 42 people were given a 3, and so on. And again, the sum of our frequencies here, we're told, is 150. So we have 150 employees. Construct a probability distribution for the random variable x, and then we're going to graph it. So your probability distribution is really just a table. That's all it is. You can do these horizontally, you can do these vertically, it really doesn't matter. Your book likes to do it horizontally here, so I'll just follow suit. And what you do is you need to have your x value and then your probability. So here our x values are 1 through 5. So 1, 2, 3, 4, and 5. And then how do you find probabilities? Well, probability is still just that idea of part over total. So just like before, when you would do a relative frequency table or a relative frequency histogram, you take that part over the total frequency. We're doing the same thing here. So for number 1, you have that 24, and you have 150 people all together. So if I go ahead and divide this out, I'm going to get 0.16. And then for the next one, you have 33 people in that group. So I have 33 divided by 150. And let's see, I get there 0.22. Next, I have 42 over 150. And I get 0.28. And then the other two are going to continue the same way. So I'm going to take the 30 divided by 150 and the 21 divided by 150. And what I'm going to get for those values is going to be 0.20 and 0.14. Now, a lot of times you have to round as well. So if you have to round your probabilities, that's perfectly fine. Just make sure you're reading carefully to see how many decimal places you would need to round to for that particular problem. So that's it. This is our probability distribution right here. Now, just to kind of talk a little bit more notation. So what you would notice here is that the probability of getting a 1 is 0.16. So just kind of that x would become a 1 if you're writing notation like that. The probability of getting a 2 is 0.22. The probability of getting a 3, right, is 0.28. The probability of getting a 4 is 0.20. And the probability of getting a 5 is 0.15. Okay, so just again, kind of bouncing back and forth between that notation probabilities and the table. Now we can also go ahead and graph this. So I'm going to go to the next page. I have the graph already done for us. So here's our graph. So notice that on the bottom here, instead of having classes or class midpoints, you just have the scores here. So our relative x values, 1, 2, 3, 4, 5, and they're basically sort of just centered on those bars. And then vertically, you have your probability. So our first one was 0.16. So you can see it's a little bit above that 0.15. Then we had 0.22, 0.28, 0.20, and 0.14. So the heights of our bars match those probabilities, which are given here on the left. Now, one last thing I want to note, because this idea really comes up more in chapter 5, but the probability of each outcome occurring actually is the area of the bar as well. So what you're going to notice for our bars in general, at least in this example, is that your width here is just a unit of 1, right? And our area of a rectangle is always length times width. So just to kind of notice that, you know, your width is 1, and in this case, our length is that 0.16. So we actually are seeing that the area of the bars equals the probability. Okay. Now this is just something I don't want you to worry too much about, or just kind of keep in the back of your mind. So with discrete probability distributions, it's doesn't make that much of a difference really for anything, because our width tends to be always 1, so it just works itself out. But we actually, when we get to continuous, we're going to see that how we find our probabilities has to do with area, the area of the graph. So this idea still holds for discrete probability distributions, even though we don't kind of stress it as much. But we do have this correlation between the area on the graph and a probability, which we're going to see this chapter a little bit, but mostly in the next chapter as well. So I just wanted to point that out. All right, let's just do a couple more examples here. So we want to verify that the distribution for the 3-day forecast and the number of days it's going to rain is actually a probability distribution. So to do that, and this was actually given on a previous page, you need to check, first of all, that each probability is between 0 and 1, inclusive, meaning that you can actually have 0 and 1, that's fine. And 2, the sum of all probabilities is 1. So those are the two things that you need to ensure that you actually do have a probability distribution. If these things don't occur, then it's not a probability distribution. So this example here looks at days of rain. So a forecaster is thinking about the next 3 days of the forecast, and they're trying to decide what's the chance that it's going to rain. So 0 means that all 3 days would be sunny. 1 means that 1 day rains and 2 days are sunny. 2 means that 2 days are raining, 1 day is sunny. And then 3 means that all 3 days are raining for the next, 3-day forecast. So this is just an example to look at. It doesn't really even matter what the data is about as long as these two things check out. So first of all, we need to make sure that each probability is between 0 and 1, and they are. So if I check my probabilities here, each of these is between 0 and 1, right? I don't have any negatives. I don't have anything bigger than 1, so I'm all set. And then I do want to make sure that my probabilities add up to 1. So you need those two things to actually ensure that you have a probability distribution. All right, so here, let's see, I have 10 and 10 is 20, so 0, carry the 2. Then I have 3, 4, 5, 6, 6 and 6 is 12, plus 8 is 20 again. Here I have 4 and another 4. It's going to give me 8, and then I have 9, 10, and I do see that I add up to 1. So I do have a probability distribution here, And everything was basically done correctly. And we can do the same thing here. So let's see if these are probability distributions. And again, it doesn't even really matter what the background is. What matters is that you can check off these two things. So the first thing we need is that each probability is between 0 and 1. So if I look at this first example, P stands for probability. All my probabilities are between 0 and 1. So that checks out. And then the other thing I need to check is I need to see if these actually add up to 1. All right, so let's see here. I have 9, 10, 11, 12, 13, 14, 15, 16, 17. Carry the 1. 3, 4, 5, 6, 7, 8, 9, 10. Carry the 1. And I'm getting 1.07 here. Now that's too high, right? Sometimes you may have a tiny bit of rounding error, right? Like if I had 0.999 or 1.001, then I could just have some rounding error. So maybe I should go back and check my probabilities and round them a little bit better. But this is too far off. So that is not 1. So this is not a probability distribution. Now for the second one, again, we check those same things. So these are the two things you're checking. And if I check the first one here to see if my probabilities are between 0 and 1, I have two issues. So I have this one right here, because 5/4 is the same thing as 1 1/4, which is 1.25, so it's too big. And then I also have something that's too small. So these two probabilities are not between 0 and 1. So these are bad. These make it not a probability distribution. These aren't even probabilities, right? So beyond not being a probability distribution, these are not even probabilities. They have to be between 0 and 1. Now, fractions are okay. I know we don't use them too often, but fractions are fine as long as they meet these other requirements.